Hello, let us continue our momentum and impulse revision. Question 1. A body at rest of mass m explodes into two pieces of masses m over 4, smaller, lighter one, and 3m over 4, heavier one. Calculate the ratio of the kinetic energy of the two fragments. Here it pays to use the formula for kinetic energy in terms of momentum. We discussed in previous classes, EK equals to momentum squared over 2 times the mass. So the total momentum before the explosion is 0. So it is 0 after as well. Thus, the two fragments must have equal and opposite momenta. This is the formula we're talking about. Kinetic energy equals to momentum squared over 2 times mass. Lighter mass, we use ml equals to m divided by 4. M heavy, so mh equals to 3m over 4. Kinetic energy of the light one divided by kinetic energy heavy one. So plug in the values. Momentum squared over 2m, mass of the light one, and p squared over 2mh, mass of the heavy one. Momentum cancel out and 2's cancel out, as the two fragments must have an equal and opposite momentum, right? So that gives us 1 over ml over 1 or more mh, and denominator flipped, mh over ml. Substitute masses, 3m over 4 and m over 4. M's cancel out, 4's cancel out, gives us 3. So the ratio of the kinetic energies of the two fragments equals to 3. Here, kinetic energy of the light one over kinetic energy of the heavy one. This is a very interesting question. A ball of mass 250 gram rolling on a horizontal floor with a speed 4 meters per second hits a wall and bounces with the same speed as shown in the diagram. A. What is the magnitude and the direction of the momentum change of the ball? B. Is momentum conserved here? Why or why not? So let's take a look at incident momentum here. So that is Pi, or initial momentum. So initial momentum, the impact is, the initial momentum has a x component and y component. X component has no impact. So we focus on y component. That is adjacent Pi cosine 45 degree. But the direction is upward direction. Remember, momentum is a vector quantity. So let us choose upward as a positive reference. So this is positive Pi cosine 45 degree. After reflected, you can see that's P final. And we will look at the y component, also adjacent, but in opposite direction. So that is going to be Pf cosine 45 degree, but minus because the direction is opposite direction, as momentum is a vector quantity. So change in momentum equals to final momentum minus initial momentum. And here we are looking at only the y component, which actually contribute to the impulse. That is minus Pf cosine 45 degree final momentum minus initial momentum. Remember, final momentum is opposite direction, so it's a minus value. Plug in the values. Minus, mass is m, velocity is v, and mass and velocity is not changed, right? It's a ball of mass rolling on a horizontal floor with a speed v, hits a wall and bounces with the same speed, but opposite direction. The momentum is same, but in opposite direction. So we have a, since the momentum is a vector quantity, so we have a minus 2 times mv cosine 45 degree. Let us plug in the values. minus 2 times the mass is 0.25 kilogram times the velocity is 4 times cosine 45 degree. That gives us minus 1.41 ns. We choose upward as a positive direction, and we get a change in momentum is minus. That indicates the magnitude of the change in momentum is 1.41 Newton second, but the direction is downward direction as we have a minus sign. Is momentum conserved here? Why or why not? It depends on what we take the system to be. If the system is just a ball, then its momentum is not conserved, since there is an external force acting on the ball from the wall. If, on the other hand, we take the system to be a ball and a wall, in a closed system of the ball and the wall, then the total momentum is conserved, since there is no external force acting on the system. The wall will acquire a momentum equal and opposite to the momentum change of the ball, and action and reaction pair here. Question 3. A ball of mass m is dropped from a height of h1 and rebound to a height of h2. The ball is in contact with the floor for a time interval of t. Show that the average net force on the ball is given by. So let us visualize. Initial height is h1, speed is v1, and then speed v2, and change to height h2. So mg h1, initial gravitational potential energy just before hitting the floor, kinetic energy after bouncing, kinetic energy, and reach new height, mgh2. So based on the conservation of energy, mgh1 equals to 1 over 2 mv1 squared. M's cancel out. We get this. Both side times 2. We get 2gh1 equal to v1 squared. Both sides squared. We get v1 equals to 2gh1. We do the similar after bouncing. 1 over 2 mv2 squared equals to mg h2. M's cancel out, and both side times 2. We get this, which is equals to v2 equals to root square of 2g h1. Net force equals to rate of change of momentum, which is final momentum minus initial momentum divided by time taken. Velocity is a vector quantity, so we choose upward as a positive reference. Then the v1 is moving downward direction. So v1 equals to minus root square of 2gh1, and the v2 is upward direction. So v2 equals to plus root square of 2gh2, as momentum also vector quantity. So we obtain this expression. Now we need to plug in the values. So velocity 2 is positive, as it is upward, and the minus root square of 2gh1, as velocity 1 is downward direction, so that's negative. And minus becomes plus. We get m times root square of 2gh2 plus root square of 2gh1 divided by t, and we showed that the average net force on the wall is given by this expression. B, if h1 8 meter, h2 6 meter, t equals to 0.125, and m equals to 0.25. Calculate the average force exerted by the ball on the floor. So let's visualize the force acting on it. On the floor, it has weight downward and reaction force upward. F net equals to m times root square of 2gh1 plus root square of 2gh2 divided by t. The F net equals to mass is 0.25 times root square of 2 times acceleration due to gravity 9.81 times the first height is 8 meter plus root square of 2 times acceleration due to gravity 9.81 times the second height is 6 meter divided by time taken 0.125. That gives us 46.8 Newton. And net force equals to reaction force minus the gravitational force. the question is asking the average force exerted by the ball on the floor, which is a reaction force. Reaction force equals to mg plus net force. Mass is 0.25, acceleration due to gravity is 9.81, plus the net force 46.8. That gives us 49.2 Newton or 49 Newton as two significant figure. Two mass of 2 kg and 4 kg are held in place, compressing a spring between them. When they are released, the 2 kg moves away with a speed of 3 meters per second. What was the energy stored in the spring? Initially, smaller mass plus larger mass, and it is stationary, so initial velocity equals to 0. Mass of the small one, mass of the large one. So to the right is positive reference, then to the left is negative. So the small mass is moving to the left. So V1 equals to minus 3 meters per second. And we would like to find velocity of the larger mass. The initial momentum is 0 and will remain 0. Therefore, speed with which the 4 kg moves of is can be found from conservation of momentum. Total mass times U equals to m v1 plus m v2. Initial momentum is 0. 2 times minus 3 meters per second as velocity of the small mass moving through to the left, plus m. Larger mass is 4 times v2, and the v2 equals to 1.5 meters per second. That means the larger mass moving to the right. So now the total kinetic energy of the two bodies equals to 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. So that's the total kinetic energy. 1 over 2 times 3 squared plus 1 over 2 times 4 times 1.5 squared. Energy is scalar quantity. So that's 13.5 joule. So we found total kinetic energy, and based on the conservation of energy, elastic potential energy converted into a kinetic energy of the two masses. Total kinetic energy is the energy stored in the spring, which is 13.5 joule.